Welcome to 3.1. This is functions of more than one input, where we are going to start to get away from the vector calculus, and now we will start to do functions of non-vector calculus functions, where there are more than one input, but there exists only one output, like this. So first of all, a review. The single variable functions look like this, right? Obviously, you already know. The output is f of x, or f. That's what we usually say. F is the output, and x is the input. And the rule that the x must go through, the rule that the input must go through to become the output, sometimes you see it like this. It's a little bit of a weird notation, but x basically is saying x turns into x squared plus 5x plus 6, right? And that's a single variable function. That's normal. Vector functions look like this, right? R of t, or, well, r of t, and then you have x of t, y of t, and z of t, which means each of them can be rules. I mean, you could have like 2t, sine t, and cosine t, and these would be rules, right? So these would be rules. So these would be rules, and these are the outputs. X, y, and z are your outputs, and t is your input. So it's three functions depending on one function, right? And usually we just put the r with a vector sign on top to indicate it as a vector function. You should already know this. It's from last chapter. Next, these are your new functions. They are functions of more than one input, and the number of inputs you can see in the function, and you can also see how they are structured, how the notation is, or what inputs are in there. So in this case, it will be f of x, y. So for the rule of f, takes in two inputs and spits out one output, f. So f of x, y is what I'm going to call this. Some people might call it f of x comma y. Makes sense as well, but I'm going to call this f of x, y. So f of x, y is equal to x squared minus 2xy plus y squared, right? So to evaluate, you simply just plug in. If it's f of 2, then it will just be, well, 2 squared minus 2 times 2 times 2 plus 2 squared. F of 4, negative 1, 4 squared minus 2 times 4, negative 1 plus negative 1 squared, right? So all the x's you replace with the left number, and all the y's you replace with the right number. Simple, not very hard. Next is find the domain of these functions and evaluate it at x equals 2, y equals ln of 2. So what is the domain of these functions? Well, domain works the exact same way. Usually you'll see it in set builder notation like this, x, such that x is equal to whatever. You can also see it like this, x belongs to the real numbers such that x is whatever, but we're just going to say x such that x is whatever, right? Or y such that y is whatever, or whatever relationship between the two, to use the domain. So for example, in this one is natural log x to the 1/2 is natural log square root of x, and natural log of x can't be like the domain for natural log is 0, open bracket, so it can't include 0, open bracket 0 comma infinity, right? It cannot include any numbers that are less than 0, and y, well, the y value does not matter. So what you actually get is x and y such that x is or y is all real numbers, but x has to be greater than 0, and I think that's it, right? And if you want it more clear, x and y both belong to the real number, the set of the real numbers, such that x is greater than 0. That's your domain. And to evaluate it, it's simple. It's just f of 2 natural log of 2 is equal to e to the natural log of 2 multiplied by natural log of e to the or 2 to the 1/2, which is e to natural log of 2 is 2, and then natural log of square root of 2. That's it. Simple. Very, very simple. Or it could also be equal to natural log of 2. That's it. Because the 1/2 can go out of the fraction, because that's a rule of exponents, or the rule of logarithms. The 1/2 can go out of your function, and it can multiply by the 2 to get you 1 natural log of 2. Now try this, f of x, y, x arc sine x. So for this example, arcsine, the domain is actually only negative pi over 2 to pi over 2. That's your domain, right? Actually, no, that's not your domain. I'm sorry. That's the range. The range is negative pi over 2 to pi over 2. The domain is 0 to 1. Yes, okay, so the domain is 0 to 1, or negative 1 to 1, I'm sorry, okay, the domain is negative 1 to 1, so what you get is, this is x belongs to the, or xy, but there's no y in the function, so it doesn't matter, so x belongs to the real numbers, such that x is greater than, or no, not greater than, negative 1 is less than or equal to, x is less than or equal to 1. And that's your domain. Now evaluate it at x equals 2 and y equals natural log 2. There's no y in the function, so f of 2 natural log 2, or I'm going to use the fancy L, natural log 2, is 2 arcsine of 2, which does not exist. Does not exist. So setting these equal to each other is actually wrong. It's undefined. And that's your answer. F of 2 natural log 2 is undefined. It's not 2 arcsine of 2. It's undefined. Find the range of the function z equals 9 minus square root of 9 minus x squared minus y squared, and sketch the graph. So z can be equal to f of x, y, right? So if I do f of x, y is equal to z, that will look just like a, oh god, that's a stinky, poopy color, a 3D graph, like this, but with a z component. I will not stop. Okay, there you go. Nice. I finally hit the center. So, what's the domain of this? Well, first of all, we need this to be equal to, we need this thing in the square root to be equal to 0. We need, specifically, we need it to be more than 0. But if we set it equal to 0, then we can find out when it's more than 0, when it's less than 0, and so on. So if you solve it, you'll get x squared plus y squared is equal to 9. So what does this mean? X squared plus y squared equals to 9 means that this is your kind of range. That's your range of, or no, this is your kind of domain. So that's the area within where you have to be less than, because if it's more than, right, this is 9 minus x squared plus y squared. If it's more than 9, if x squared plus y squared is more than 9, then it will tip over and the number inside the square will be negative. So you got to make sure that it's not greater than 9. So in fact, it's less than 9. Less than or equal to, because it can still be 0. Square root of 0 is still 0. So that's totally fine. But x squared plus y squared is less than or equal to 9. It's really the main thing about this function. However, that's not what we're trying to ask for. That's the domain of the function, not the range. So what is the range of the function? Well, this is the lowest we've said so far, right? That's the lowest. And if you think about it, just think about it a little bit, and then tell me what the highest value of the function can be. 3, 2, 1. Yes, it's 3. So the highest value of the function is 3, because x squared and y squared can never be negative, right? They both can't ever be negative, and you're subtracting a number that can never be like if you're subtracting a number that can never be negative, you're not adding anything. So the lowest that the number can go is 0. Right? So 9 minus 0 is what we're saying, which is square root of 9, which is 3. So the range is, I'm not sure if this is the right notation, but I'm just going to use it, f, where 0, f, and make sure it has the functions f such that f is between 0 and 3 inclusive. And that is your range. Right, so what does this look like? What does it look like? Well, so if you expand it, if you did z squared equals 9 minus x squared minus y squared like this, you will get x squared plus y squared plus z squared equals 9. If you solve it for for one of our ways, one of the ways that we want to, one of the forms that we want to see it as, like in the quadratic equations episode 1.4 of this series, x squared plus y squared plus z squared equals 9 is a familiar function. It's an ellipsoid, but it's actually a special type of ellipsoid called a sphere, right? It's a sphere. But our range is only from 0 to 3, and the sphere usually covers a range of -3 to 3 if we write in this form. So what do we have to do? We have to only restrict it to the top part of z, right? So f is z. So z is equal to f of xy. So we can only restrict it to the top part of z. So I'm going to do x, y, and z right here. So all of this bottom part of the sphere is pointless. Right? This bottom part of the sphere is pointless. There's no sphere down here. We have to only take the top part of the sphere, and I'll use a different color. Right? Something like that. Something like that. And then a circle like that. And that is the only part of the sphere that we're going to take. So that is your graph right there. That is your graph. The range is 0 to 3 because 0 is where it stops at the xy plane. Right? If you plug 0 into this function, you will see that it's a circle of radius 3. Right? And this is a sphere of radius 3. Right? So this is one of the types of equations that you are going to have to remember if you are asked to sketch it. All the quadratic equations from 1.4 and all the equations of a plane from 1.3. Cylinders from 1.4 as well. You should know your basic 2D graphs still, but certain manipulations of those, domain manipulations, range manipulations like this in the example, right? It helps to know them, and you probably won't be asked to graph many things because it's really hard to graph. This doesn't really look that nice. As you can see, it looks like one of those hats. I don't remember what cartoon it is, but it looks like one of those hats with a windmill on top of it. It looks really weird, but it's not a very nice drawing, right? It's just not a very nice drawing, right? So yeah, this is what I've been saying before. So this is you can visualize functions of more than one input in a graph like this, where z is equal to f of x, y, right? So whatever x and y function will determine z. For example, we have a point right here. You can shoot it up, and then you can see its z value is around right here, right? It's a little bit hard to see because it's a 3D plane and or 3D space, and I can't draw 3D and 2D. That's really hard to draw. So what we actually do is we use level curves. What are level curves? These are level curves right here. This is a level curve, right? And in fact, I'm probably going to look up something a little bit better to see, like a topological map, right? Topological map level curve. So I'm looking that up right now, and I will show you something like this. Okay, right? Let me paste it right here, like this. Right, so you can see all these curves right here, and they represent the elevation, right? So maybe This is 6200, right? You see 6200 right here? That's 6200. This is probably a little bit higher or a little bit lower, a little bit higher or a little bit lower, right? So once you go up and up and up, and when this loop closes down on itself like this, smaller than any other loop, you would know that you have come to the highest point or the lowest point of the graph, right? And the more closely packed that the lines are, the steeper the slope is, right? Which is how we're going to be able to tell slope due to these contour maps. Yeah, that's also what they're called. They're called contour plots or contour maps as well, right? These are level curves. These are the level curves, and then the combination of level curves put into this map is called a contour plot, right? So these are more examples of the contour plots that we have. So this is f of x y equals 1 minus x squared minus y squared, which is a paraboloid that's shift elliptical paraboloid that's shift 1 up, and it's kind of flowering out like a parabola on all axes. Yeah, that you can see pretty much. If you take a cross section, you'll get a parabola, right? And this is what the plot looks like. This is what the plot looks like. At f equals 1, there's just 1 point, because that's where f is equal to 1, right? At 0, 0, and then a circle of radius 1, you get a circle of radius 1 at f equals 0. You get a circle of radius 2, or radius root 2 at f equals -1, and it actually becomes more and more concentric. And if I were to draw another circle, it would be a lot closer as well. And you could see it's going to go farther and farther and farther. The farther it goes from the center, the closer it is, because the more steep it gets, right? That's how the level curves work, right? And you can visualize the level curves right here. If we are to just see a bird's eye view, like if you were to see from the z-axis from here, you would see that the level curves. Wait, first of all, you would see a circle, but second of all, you would see level curves like this if they were clearly marked on the map, like this, right? So you just see the xy plane and these level curves with the circles on them, right? And these are some more examples, like f of xy equals x squared minus y squared. I didn't bother drawing this. This is a hyperbolic paraboloid that we saw, the Pringle from 1.4, and there's some pretty interesting stuff, like this cross right here. You will see this cross, and this is a kind of special thing that you will see. You will see this cross in a saddle point, right? So if I were to draw the hyperbolic paraboloid again, you will see what a saddle point is. It's basically in one axis there's a parabola pointing up, on the other axis there's a parabola pointing down. So if you go in one direction, it's the minimum, but if you go in another direction perpendicular to it or whatever, it's the maximum. So that's what a saddle point is, and the cross on the contour plot indicates a saddle point. Other than that, you'll have, right, and well, another indication of the saddle point is the level curves on the horizontal axes, or the x-axis. Like as you move towards x is positive, and as you move towards y it's negative. That's another example of y is a saddle point, right? Because it moves up on the x-axis and moves down on the y-axis. So it becomes a minimum on the x-axis and a maximum on the y-axis. F of xy equal to -y. Very simple graph. It's actually just, I could draw it probably right now. If that's x, that's y, and that's z. Then f of xy equals -y is just z equal -y, which is like that, and then it would just be a big plane. We call it a cylinder, but it's really a plane. If it's just a linear line, cylinderized, then it's just a plane, right? So that's a plane, and you could see that at f equals 0, the xy plane is, well, this will be x and this would be y. So at f equals 0, the y is, or the x stays still, and the y is 0. If f equals -1, then the y is positive 1. Yeah. If x is -2, then y is positive 2, and etc., etc. Right. So a function of more than 3 variables cannot be represented on a graph very nicely, but it can like you can still draw it on a contour, although it would be a very messy contour like this one I drew right here. This is an extremely messy contour, but well, I hope it works, that if you have f of x, y, z, there's 3 variables this time, f of x, y, z is equal to x squared plus y squared plus z squared, then you can show that x squared plus y squared plus z squared equals 1. F equals 1 right here, f equals 4 right here, f equals 9 right here. I'm using these because these are 1, radius of 1, radius of 4, radius of 2 I mean, and radius of 3 respectively, so I don't have to draw super close spheres to each other, but yes, they should get steeper and steeper as you visualize, if you can even visualize in 4D space, right? For any alien that's watching this video right now and can visualize in 4D space, W equals f of x, y, z. If you have a fourth axis, you can draw W equals f of x, y, z. That will be the fourth dimension, and you can take your x, y, and z, and you will see that it's getting steeper and steeper on the W axis, right? We're not aliens, but if you are one from a different universe, then enjoy the lesson on multivariable calculus, I guess. Find a domain. Okay, another domain question, 2 more domain questions. Let's do the bottom one. Bottom one's easy, right? I hope. It is x, y, z, and such that I'll let you fill in the rest. Okay, time for me to fill in now. So x squared plus y squared plus z squared has to be less than or equal to, or no, not less than or equal to, I'm sorry, greater than or equal to 0. That's it, right? You don't even really have to do anything else. You just have to notice that this has to be greater than or equal to 0, and that's it, right? This one's a little bit different though. This one's a little harder, right? So ln of y minus z, first of all, if you look at this bottom one, you can automatically tell that, well, this is y and z, right, belong to the real numbers. I guess I can write that as well, belong to the real numbers. That's really messy. Belong to the real numbers. There you go. And then y and z belong to the real numbers. Y squared minus z equals 0. Or not equal to 0, right? You could write that, or you could actually just write y squared is not equal to z, right? So there's 2 conditions on this. The natural log, y squared is not equal to z, but the natural log presents another condition because y and z, y minus z then cannot be equal to 0 or a negative number, so y has to be greater than z, and that is your answers. That is your answer for these 2 questions right here. So that's it. That's gonna be it for today's episode. I might do a little bit more. The test for the first 2 chapters, I should have it up by the time this video is up. I will have it up on last unit. Yeah, so the last video of the chapter, the last video of chapters 12 and 13, or chapters 1 and 2, 12.3, you will see the test, and you will take the test, and tell me how you got. Just message me on Discord. I will probably leave my Discord tag down there. Probably shouldn't, but I will, for you to check out, and I will see you guys next time.